gold's superheating mystery, breaking the entropy catastrophe limit. Imagine taking gold, a metal known for its reluctance to melt, and heating it to temperatures hotter than the sun's surface, while keeping it solid. Sounds like science fiction? Welcome to a revolutionary experiment that's rewriting the rules of heat and matter. Scientists achieved the unthinkable by superheating a gold sample to 19,000 Kelvin, 33,740 Fahrenheit, a temperature so extreme it dwarfs our sun's surface, and pushed the metal to 14 times its melting point. The kicker? It didn't melt. This breakthrough challenges a 40-year-old prediction that solids can't superheat beyond 3 times their melting temperature, an idea physicists called the entropy catastrophe. Researchers now show that with ultra-fast heating, there might be no practical limit to how hot a solid can get without melting. Here's how this mind-bending experiment works, and why it's sparking both excitement and controversy in the scientific community. To achieve this, the team used an ingenious but simple approach, zapping a 50-nanometer thin layer of gold with an ultra-intense laser, then measuring the vibrations of its atoms through reflected X-rays. Those vibrations acted like a natural thermometer, allowing scientists to directly measure temperatures that would be practically impossible to read using conventional methods. This marks the first time such extreme temperatures in a solid material have been accurately measured, a method that promises to revolutionize our understanding of warm, dense matter, the incredibly hot, pressurized material found in planetary cores and fusion reactor experiments. But here's the twist. The entropy catastrophe, a theoretical limit from the 1980s that claimed solids would spontaneously melt at around 3 times their melting point, has seemingly been shattered. The gold sample was heated to 14 times its melting point from 1,300 K to 19,000 K and survived. Scientists achieved this through ultra-fast heating, blasts that lasted just 45 femtoseconds, a time frame even shorter than the blink of an eye. This speed might explain why the gold didn't melt. By heating it faster than atoms could expand or disorder, researchers essentially froze time at the atomic level. The second law's disorder increases over time principle still holds. It's more like successfully skyscraping in zero gravity while you're still getting yourself strapped in. The question now becomes, if speed truly lets solids dodge melting, what other theoretical limits might be oversky when we leave behind our slod-hindered ways of heat transmission? For researchers like Oxford University's Sam Vinko, this raises bigger questions. Could we theoretically cheat thermodynamics by simply being quick enough? This kind of thinking could rewrite our understanding of material science and energy applications, like fusion reactors. As SLAC scientist Bob Nagler emphasizes, the real lasting impact may be the new measurement technique developed, a game-changer for studying extreme states of matter that previously defied precise analysis. However, not all scientists embrace this interpretation. Some point out that the entropy catastrophe isn't a fundamental physical law, but rather a statistical prediction about equilibrium states. The argument becomes philosophical. Does this experiment truly beat thermodynamics, or does it exploit a loopholes by operating outside the timescales for which those predictions apply? This is where the debate gets fierce, and where you, the reader, get to join in. Would you say this experiment challenges established science, or does it highlight clever workarounds within its boundaries? Share your thoughts in the comments below. What happens when you blow up gold? The science behind it. Think gold is indestructible? Science just proved it can survive the impossible. What happens when you blow up gold? You don't get ash or melted sludge. You get gold, just in microscopic shards. Historians and alchemists obsessed over gold's invincibility for centuries. But recent experiments reveal shocking truths that bourgeois physics as we know it, and why the metal's future in tech could be more explosive than ever. So, what makes gold the ultimate undestroyable? Material? Its atomic structure remains intact even after melting and reforming countless times. Imagine heating a gold bar to its 1948 degrees Fahrenheit melting point, then letting it cool back into its original shape. Repeat this process 1,000 times. The gold remains pristine. But scientists wanted to push it further. Enter the SLAC National Accelerator Laboratory's laser experiments that blew traditional theories to shreds. Here's the controversy. For decades, physicists believed materials like gold could only reach 3 times their melting point before experiencing an entropy catastrophe, a violent disintegration. But researchers just proved gold can withstand blistering temperatures 14 times hotter than its melting point, reaching an astonishing 33,740 degrees Fahrenheit, 18,726 Celsius. How? By suppressing expansion during heating and using X-rays to analyze atomic vibrations. The result? Gold enters a crystalline limbo, a temporary state between solid and liquid that defies conventional logic. This isn't just academic trivia. The findings could revolutionize nuclear chemistry, astrophysics, and space exploration. The James Webb Space Telescope already relies on gold coatings to observe infrared signals from distant galaxies. What other groundbreaking applications await? Scientists speculate about new materials combining gold's properties with other elements, suggesting potential breakthroughs in electronics, energy storage, and even medical implants. But what does this mean for investors and tech enthusiasts? Gold's growing industrial demand, up 7% in 2024, isn't just about profit. It's about innovation. As electronics shrink and demand for heat-resistant components grows, gold's unique properties position it as essential to future technologies. The catch? Its rarity and cost could limit adoption. The debate. We'd love to hear your thoughts. Are these findings a game changer for material science or a distraction from practical applications? Share your perspective below. Unveiling the secrets of superheated gold. Beyond the entropy catastrophe, imagine gold, the quintessential symbol of stability and value, being heated to temperatures that defy all conventional wisdom. This isn't a scene from a science fiction movie. It's a groundbreaking discovery that challenges our understanding of material stability. Researchers have pushed gold to 14 times its melting point without it liquefying, revealing new insights into the extreme limits of material stability. But here's where it gets controversial. This discovery calls into question the long-held entropy catastrophe threshold, a critical point where the entropy of superheated crystals is equal to that of their liquid counterparts. In a study published in Nature, researchers used ultra-fast laser heating and high-resolution inelastic X-ray scattering to explore the extreme limits of gold's structural stability. This method allowed them to delve deeper than ever before into the behavior of gold under extreme conditions. The findings are nothing short of astonishing. Gold retains its crystalline structure even at temperatures of nearly 19,000 K, over 14 times the metal's standard melting point. This challenges the previously assumed entropy catastrophe threshold, which suggests that a solid should become thermodynamically unstable once it approaches about 3 times its melting point. TM. The team aimed to experimentally test this long-theorized upper boundary of superheating. Advances in short-pulse laser technology have enabled scientists to reach heating rates exceeding 10 to the power of 14 Kelvin per second, bypassing the slower, destabilizing processes that typically lead to melting. Previous experiments had superheated gold to between 1.4 and 2.1 TM, but this study went further. By using inelastic X-ray scattering to directly measure ion velocity distributions, the researchers overcame the limitations of indirect methods used in earlier work. This provided modeling-dependent access to lattice temperatures, offering a clearer picture of what was happening at the atomic level. Gold films just 50 nanometers thick were irradiated with ultra-fast laser pulses, achieving heating rates above 1015 Kelvin second. At 3.5 times 1015 Kelvin second, samples reached 13,800 plus 3,200 Kelvin, around 10 TNAMs. At 6 times 1015 Kelvin second, the temperature peaked at 19,000. Surprisingly, the Bragg peak positions remained fixed, indicating no significant expansion or ablation. This stability contradicts expectations from entropy models, which predict rapid breakdown once the entropy of the solid phase exceeds that of the liquid. The researchers used a multiphoton expansion approach to precisely model the scattering during heating. They fitted Voigt profiles to experimental data via maximum likelihood estimation. Electron thermal properties were also modeled to confirm uniform heating. Under experimental conditions, electron thermal conductivity was estimated to be between 3,000 and 5,000 watts per kilogram, and heat capacity around 0.3 to 0.5 joules per kilogram, leading to a thermal diffusion time across the 50 nanometer sample of about 0.5 picoseconds. These conditions supported the assumption of near instantaneous uniform electron heating across the sample. Laser fluence was adjusted using an iris before the final focusing optics, allowing the researchers to control and isolate energy delivery. Only scattered X-ray photons, corresponding to known fluence bands, were included in the temperature analysis. Temperature and structural measurements were taken simultaneously using Diopta's software to process X-ray diffraction patterns. The study's most striking result is that the system avoided the long-assumed entropy crossover point, where the solid's entropy overtakes the liquid's. This threshold has long been considered a thermodynamic ceiling for solids under heat. But by heating fast enough to suppress expansion, the researchers showed that gold can remain stable well beyond this point. The entropy of the solid phase stayed below that of the liquid at all temperatures achieved. This suggests the entropy catastrophe may not be a true upper bound, at least not under ultra-fast heating conditions. Because the heat capacity of the solid under these extremes is governed by universal constants, and the liquid phase is still purely characterized, the point at which entropy curves cross remains uncertain. Deviations in heat capacity for non-equilibrium systems and thin films may also shift the entropy balance. These findings suggest that, if the heating is fast enough, the predicted limit for superheating can be exceeded by a wide margin. It may not exist at all. The crystalline structure of gold withstood temperatures that conventional thermodynamics says should be impossible for a solid. These implications extend beyond gold. Understanding material stability under ultra-fast, high-energy conditions could inform the design of more resilient materials for extreme environments, such as those encountered in nuclear fusion, astrophysical research, or ultra-fast electronics. And this is the part most people miss. The study challenges the very foundations of our understanding of material stability. It raises questions about whether the entropy catastrophe is a true limit or just a theoretical construct. What do you think? Could this discovery lead to new materials that defy our current understanding of thermodynamics? Share your thoughts in the comments below.